All right, welcome. Thanks for coming. My name is Rick Kutzpel. I'm a product planner at Broadcom's Data Center Solutions Group. I have product responsibilities within DCSG where I watch market trends, different things within the industry to help guide our roadmaps, and then also shepherd our products from roadmap into development and then ultimately into production. I also run our Drive Alliance program where we partner with many of the key drive vendors within the industry where we exchange information, we exchange roadmaps, make sure we're aligned on technology transitions, things like that. We also do quite a bit of testing, early physical layer testing, all the way into production with AVL testing, and then also some customer issue type testing. On top of all that, I coordinate the majority of storage standards work within Broadcom, where I'm on the board of directors of the SCSI Trade Association. I've been involved in enterprise technology markets for nearly 40 years with roles in hardware design as well as marketing, and a little more than 20 years of that has been dedicated to enterprise storage. With me today, I have Madhavan Ravi from Meta. Madhavan is one of the most recognized storage contributors within OCP and is a hardware system engineer responsible for designing and deploying storage hardware for exabyte scale distributed systems at Meta. His focus areas include hardware architecture, storage system efficiency and performance, and storage for AI applications. Last year at SDC, I spoke on some of the innovations and investments being made in SAS, specifically 24 gig SAS for hyperscale architectures. And so I'm going to kind of recap that real quickly today. But what I really want to focus on is how SAS is being used in hyperscale architectures today, modern hyperscale architectures. And I want to focus on a couple key areas. I want to focus on scalability, reliability, flexibility, and cost. So to kind of recap from last year, I hit on a couple of the main innovations and investments in SAS, and shingled magnetic recording, or SMR. It's about increasing the areal density of a drive, having the same drive with more capacity. Next generation SMR, sometimes will be referred to as SMR 2.0, hybrid SMR, a couple different names, but it has been moved into T10, and it's all about being able to format a drive in different manners. So reducing the number of SKUs the data center has to manage, and then have them format the drive either in a conventional manner or in a shingled manner, or some split of both, and then to be able to do it dynamically. And then repurposing depopulation, or depop. This one's interesting. It's about being able to depopulate a head or a platter that is having problems. What the drive vendors have found is that a large percentage of the returns that they get, of the failed drives that they get, are all related to a single head or a single platter. So if the drive can then depopulate that particular media, then the drive can continue working without disruption to the data center. And so it's interesting because it not only reduces the number of spares that have to be on hand, but also increases the amount of available storage in the case of one of these events. Then there's multi-actuator. This has been in the news quite a bit, having more than one actuator within the HDD. It's targeted mainly at performance, but very specific performance. It's really performance per capacity, or IOPS per terabyte of the drive. And then command duration limits. You might have heard this be referred to as OCP fast fail. T10 rebranded it as command duration limits. And it's a technology to help control the tail latencies of the HDDs, specifically increasing queue depth without sacrificing those types of things. And so for more details, I encourage you to go to the SDC archives. My last year's presentation, it goes into quite a bit of detail on all of these. Now I want to shift to why modern hyperscale architectures are using SAS. As I mentioned, I'm going to focus on a couple key things: scalability, reliability, flexibility, and cost. Scalability plays a really large, important role in hyperscale architectures when it comes to handling and managing massive amounts of storage. For this discussion, I want to focus in on two pieces. One is the raw capacity, or the raw scalability, and another one is the dynamic capacity. The raw capacity is pretty straightforward. For most modern hyperscale architectures, to accommodate large social network infrastructures, shopping networks, the amount of nearline storage is absolutely enormous, and SAS does a great job at that kind of stuff. But to understand the dynamic scalability, we got to dig a little bit deeper. And I break it up into a couple key pieces. First, just the raw growth. If you look at social networking, everybody uploading their videos and personal content, or maybe surveillance where data is just always coming in, the amount of capacity required is always growing. And that capacity has to be continually added in a very non-disruptive, transparent method. And SAS does that very well. Storage management agility. This one's interesting because most data centers have to be agile to handle their fluctuating workloads, new applications. There's always new things coming in and out, hardware and software. And to be able to accommodate that, storage is always being reconfigured and moved around. Whether it's physically or logically, that all has to be done, again, transparently to the overall data center. SLAs, service level agreements, right? This is a really important one from a data center perspective. They're running a business. They have customers, and they have to have certain agreements with these customers. And so it's very important that they're able to keep up with those. And so as things get optimized and reconfigured, the storage does as well. And so that all has to be done in a very seamless manner. And then finally, cost optimizations. This type of scalability allows organizations to optimize costs by scaling the storage infrastructure to make sure that certain areas aren't over-provisioned. Right? If you're over-provisioned, then you're not utilizing that capacity. And then on the flip side, under-provisioning, right? If you're under-provisioned, then you have bottlenecks, and that doesn't work either. So again, it's the ability to reconfigure the systems on the fly, and non-disruptively. So how does SAS do it? SAS provides the scalability required. Like we mentioned, these types of things are all key attributes to the data center, and SAS handles this very seamlessly. SAS being connection-based can handle up to theoretically 64,000 devices. In practical limits, it's more closely aligned to 2,000. We see deployments very commonly well in the excess of 1,000 drives per domain, and then many, many copies of those, of course, in the data center. These devices in these topologies are initiators, could be an HBA or a RAID card, could be an expander, or target devices. And the target devices, right, they could be HDDs, they could be SSDs, and in the data center they could even be tape, right? And so it's very important to be able to accommodate a large number of these. These targets then can be added and removed either individually or in full enclosures, again in a non-disruptive manner, running IOs, and you can just be able to reconfigure the system either at the drive level or an enclosure level in a very non-disruptive manner. Another aspect of scalability is distance. SAS supports active cables, both active copper and active optical. The active optical cables give you distances well in the excess of 100 meters. And therefore, SAS does a great job inside the rack, rack to rack, and then also within a campus. oops. Yep, reliability. SAS was originally developed and designed to meet the needs of enterprise-grade storage requirements, where data availability, the access to data all the time, and data integrity, the fact that data corruption is absolutely not accepted, was critical in 24/7 type deployments. So SAS was built on those premises. And its features like, native dual path support, forward error correction, like that was added in 24 gig SAS with the 20-bit Reed-Solomon algorithm, end-to-end data protection, and advanced management features like self-monitoring, analysis, and reporting technology, or some people refer to it as smart technology, all go into making SAS a really reliable feature. And at the scale of some of these data centers where it's racks and racks and racks, right? Reliability at any level starts to become a really big deal, and it will ultimately end up. We'll talk about that in cost as well. Then there's the flexibility. So the flexibility that the SAS protocol provides is important to the data center deployments, because it not only supports SAS HDDs and SAS SSDs, but also supports SATA HDDs and SSDs. And some of the recent investments and innovations in nearline storage, like SMR, like CDLs, and like DPOP, to mention just a couple, make a strong case for HDDs, and more specifically SATA nearline HDDs. SATA nearline HDDs today have about a 6x price advantage over comparable SSDs. So at the scale of some of these data centers, that starts to become very, very significant. It should be noted that traditionally SATA was designed as a client technology and had some pretty significant limitations. But what SAS, with the addition of STP, or the SATA tunneling protocol, it now can provide connectivity of in the excess of thousands of SATA drives, again making it very well suited for the data center. Cost is really where rubber meets the road. We just got done talking about the importance of the data center of scalability, reliability, and flexibility. And now we're going to switch to cost. And what you'll see, it's kind of interesting because each one of those then has ties back into cost, and we'll talk about some of those. To look at the cost, we need to break it up into two pieces. We'll talk about the total cost of ownership, and break it up into CapEx and OpEx. First, we'll look at CapEx, and probably the largest ticket item is the cost of the media. It's surely not the only one. There are going to be others, but we're going to focus on that one as it's probably arguably the largest one. We're talking about the cost premium or the price premium of SSDs, specifically QLC SSDs, over nearline HDDs. And as you can see from this chart, it was, in the past it's been well in the excess of 10x. But if you look at this data, and this data is from IDC, dated April, if you can't see the small writing, you'll notice a couple things, and you really have to take heart to a couple key variables here. The first is NAND pricing, right? NAND pricing plays a huge role in this, and right now we're in unprecedented times with the cost of NAND and some of the capacity issues that the NAND suppliers do have, and so those prices are dropping very dramatically. That's why you see the drop down in the 6x type range in 2023. Moving forward, some assumptions have been made about pricing moving forward, but that's a huge variable. That makes a swing, back up to be more normalized, and this chart will change significantly. Another one is with regard to assisted recording technologies, right? If HAMR can be productized in a reasonable fashion and meet its hyped value proposition, and it will deliver, say, 32 terabyte drives in the near future and 44 terabyte drives in the 2025 timeframe, this chart will start looking very different. Right now, this data is assuming that those type of technologies do not come to fruition in this timeframe. So how does this translate into real deployments? If we look at the most recent trend focus data, and notice this was updated in August, so this is very recent data. A couple things jump out at you. First, notice that this is enterprise storage capacity, and I define enterprise storage capacity as enterprise plus the data center, and then do it by capacity by device type. And you'll notice the orange bars are nearline HDDs, and then you look at the amber piece, and that's enterprise SSDs. That includes NVMe, SAS, and SATA. So that's all SSDs. And so the first thing that jumps out at you is that today about 90% of all capacity shipped in this segment is nearline HDDs. Right, that's an enormous amount, and that trend's largely going to continue. The amber bar, the SSD bar does grow over time, but from a raw capacity perspective, it's anticipated that it's going to be largely dominated by nearline HDDs. The other thing is the correction, or what we're seeing in 2023. In 2022, Q4, capacity shipments started to decline. And right now we're in the trough with expected recovery in Q4 of this year, and then going back to a relatively regular growth rate. The one thing that has changed since the January forecast is if you did a five-year CAGR on the capacity shipments, it was growing at about 30%. Now with this adjustment, now we're at about 20%. So the forecast is down from a shipment perspective, but it is supposed to it's still going to continue, and 20% is still a relatively large compound annual growth rate. So then that brings us to OpEx, where arguably the two largest contributors are staffing and power costs. Staffing, we talked about that a little bit ago with talking about technologies like Depop, right? If you can keep staffing levels low, especially at this scale, right? That's a big advantage. But what I wanted to focus on is really more around the power costs, and you can pick up, if you Google it, you can pick up articles of all different flavors, making arguments in either direction. So what I wanted to do is I wanted to look at it, do my own assessment. So what I did was I took two drives that are in production today. I took Micron 6500, which is a QLC SSD, 30 terabyte drive, and compared it to the Seagate 22 terabyte drive. Again, both in production. I grabbed their data sheets right off the web, and I looked at their power. You can see I took their idle power, read power, write power, and that's a start, right? That's surely not the story. So then you have to come up with workloads, and in some of the analysis you see they just say, okay, read intensive is 100% reads and write intensive 100% writes. That doesn't really imitate the real world in a data center. Now there's a lot of flexibility, and you could mix the numbers in many different ways. For my analysis, what I did was I assumed that half the drives were idle. The other half, like for the read intensive version, 45% are reads and then 5% are writes. And then the complementary for the write intensive power workload. And you can see in those, we boil it down, but that's, in my opinion, that's not the whole answer, because we're looking at the power per slot, and you have to also keep in mind the capacity of that slot. And so if you normalize it by capacity, on the Micron side, we normalize it by the 30 terabytes, and the Seagate the 22 terabytes. You can see those numbers. On the read side, it's about a wash. The math comes out very similar. On the right side, there still is a considerable advantage for HDDs. Now, the logical question is, well, the one thing you've left off is performance. And I mean, that is going to skew these numbers considerably. However, remember, we're talking mainly about warm and cold tiers of storage, right? So if you're talking about a performance tier, performance might be of higher interest. But for cool, cold, well, even warm, it's less of an issue, and so I have not included it in this particular analysis. And with that, right? So that's my, I wanted to highlight scalability, reliability, flexibility, and cost. And now what I wanted to do is have Madhavan come up and talk about how, at his architecture in Grand Canyon, how he made some of the decisions that he made. So, Madhavan.
Thank you, Rick. I try to maintain the same themes that Rick mentioned, but I'm coming from Meta's perspective, and I won't touch on all the topics that Rick brought up, because some of those don't apply to us, but a good majority do apply. This is a very simplified block diagram of one of the use cases of a hard drive-based storage server / JBOD. The code name for the program was Grand Canyon. It was released to OCP a while ago, a few months ago actually. This is one storage use case, and I have a name called Tectonic also in brackets. You can look it up. There is a Usenix paper and a video on the architecture of the distributed storage platform. That's the storage software layer. From a block diagram perspective here, I have anything to the left of the CPU is stuff that is not related to the hard drive or SAS architecture, but we need that for supporting denser and denser drives, the NIC and the caching SSDs. To the right of the CPU, you see the SAS HBA or the IOC, IO controller, SAS expander, and between them we have 24 gig SAS on the platform. And to the right of the expander, this particular SKU has 36 hard drives. This is one half of a 4U chassis. When I look at the other SKU, a slight variation, you can say bomb stuffing options in the chassis. We enable a cold version of the same SKU. It has way more IOCs and SAS expanders and three whole chassis connected to one CPU and NIC. And this kind of daisy chaining of SAS expanders, using copper cables to connect and fan out to multiple chassis is possible only with 24 gig SAS to support our bandwidth as well as the fan out. The number of HDDs in this config is 216. And Rick touched on cost and storage. Cost is where the rubber meets the road. I can't emphasize that enough. If you think about a company like us where most of the users are using applications on their phones, backend storage is so far away from that for majority of the company, it probably doesn't matter at all. The only time it matters is when finance cooks up the quarterly financial report and you see the cost of storage spend. And there's always the question, how can I get it lower? And how can I make it cheaper? So cost is of really high importance for storage while meeting the performance needs and while meeting the reliability needs, and flexibility to enable that growth is really important to us. Another way you can look at it, Rick touched on OpEx at a power level and headcount level to support. When I have a new technology that I have to take in place of or to replace an existing mature technology, there's a lot of R&D that a company has to invest in. And you might have heard of the year of efficiency that Meta has publicized quite a bit. And I think it's going over in multiple places. This is like, he said, she said, I'm going to do it as well. But jokes apart, it's actually good financial discipline to look at what's my ROI if I invest my money in this. So that is also of prime importance. If I don't have to design a new platform to deploy the capacity that I need, it is a win for the company. It's quick to scale up. And this is something that the SAS platform, along with the way the system is architected, the Grand Canyon platform is architected, enables us to do. The cold storage queue, I'll go back to this slide. The cold storage queue is 3 servers in a rack. Each server has 216 drives. So at a rack level, it's 648 drives. The warm rack tier is 576 drives in a rack, but a lot more CPUs, 16 CPUs in a rack. At a future date, I get to the scalability part here. The CPUs are getting bigger and bigger, more and more powerful. Per core perf is improving leaps and bounds. There is Moore's law to an extent, but if you look at the popular CPU vendors and the amount of core counts they're able to stuff into the CPUs today, along with offloads that can help storage server applications, CPUs are getting beefier over time. So if we take such a large CPU, even though it may be just a 50% increase in power compared to the HDDs, we can easily stuff that beefy CPU in the server. At one point, the cold rack tier can be one CPU or a server for the whole 648 drives in the rack. Maybe it can even be 700 drives if I can remove the servers and stuff more in, right? That is possible only because of SAS expanders. Flexibility, we have had SAS traditionally has been this high reliability interface. SAS hard drives have been the high reliability interface and architecture drive option that enterprise went to. And when Meta started storage, warm storage was on SAS. And today we are agnostic. It depends on what the market can offer at a cheaper price. We go and buy it, and that's possible through the SAS IOC expander interface. And it may be pennies, but at the scale we buy it, it's certainly not pennies. Let's put it that way. It definitely improves the cost for the company. I say support for the next 2 lines, support for SMR drives and support for CDL. And CDL is something Rick touched on. This is, we deploy CMR drives or PMR drives, conventional magnetic recording drives predominantly. We are evaluating SMR drives for the capacity advantage. Along with SMR, there is a lot of right shaping. There's a lot of work at a file system level that needs to happen. Again, goes back to my ROI point. If the SMR drive's capacity is 20% increase, maybe something comes up and it makes it 30% over PMR drives, I should be ready to adopt it if my software structure is ready. So the platform allows for that. There is an aspect that I'm not highlighting, like high density drives have that whole interoperability aspect as well, which is orthogonal to SAS, connected to the protocol alone. SAS enables to touch on or take up all of these features. CDL helps us scale to utilize 100% of the available I/O of the hard drives. There are a couple of slide links below. The second one actually touches on why we are looking at CDL, why we are looking at SMR, and how does it help us. And it even shows a snapshot of the I/O utilization percentage in our data center as an average and multiple percentiles. The way we look at I/O utilization today, probably most of the cloud players too, is let me spoon feed the I/O to each drive so that I get predictable latency. When I buy a drive, I also buy its I/O, not just its bytes capacity. So if I can make use of the drive's I/O efficiently, it's much more cost optimal. So CDL enables me to schedule stuff and have the application talk all the way to the bottom layer to maximize it. Reliability side, I have only one pain point to show, but I think it's no longer a pain point for us. The switch from SAS to SATA hard drives was really hard. Any kind of I/O timeout bubbles up the bubbles up the chain. We have the CPU going to the IOC, going to the expander, and then multiple drives. If a bus reset happens on the drive, or an IoT timeout happens, or a drive hangs for some reason, or the controller is busy, let's say the kernel issues a reset. The first layer is the drive gets reset, rescan, things come up fine. If that doesn't help, the expander gets reset, the IOC has to get reset. There is a bunch of fail-safe protocols to recover that entire end-to-end chain. Even though it happens very rarely, something that hangs forever is not acceptable if it hits the user at the front end. So this was a really painful experience to roll in SATA drives and have all that error handling mechanism fiddled into the stack. But eventually it is through, and I wouldn't say it's painful anymore. Given all of that, SAS is definitely something that enables a cost-efficient and a performant platform. Forgot to touch on performant. It also enables dual actuator adoption when we deem it is necessary. That's one of the reasons we put in 24 gig SAS. If we didn't foresee a need for it, we would probably be okay with 12 gig as well. And I will stop here with more than enough time for Q&A, I guess. And those two links are references to existing presentations and talks, recorded talks. Thank you.
All right, thanks, Madhavan. That was great. It was interesting hearing Madhavan. So you can hear it from me, the pitch, whatever, but then hearing it from Madhavan, right? Of a real world implementation. That's interesting. So I'm glad we got to hear about that. And we got to highlight the scalability, reliability, flexibility, and cost aspects, right? I thought Madhavan did a good job tying all that in. So I encourage you, so we have a couple links here. I encourage you to go follow the SCSI Trade Association on SNIA.org for reference and updates. And then follow us on any one of the social media platforms. And questions?
Yeah, a question. So obviously they're using the EC, the spinning disk, the SATAs, the nearline SATAs. Have you noticed a discernible difference between your JBODs when you're implementing SSDs? I know it's a tough balance. Your equations and your charts show the performance value, but not necessarily the throughput aside of that. But is that significant for the end user experience for you when you switch over? Do you notice anything? Because the cost is enormously different for
I take it's for me. So when you say SSDs in the same JBODs, are you talking SATA, whatever SSDs? So SSDs instead of HDDs, right? That's what you're looking at. So this is
non-spinning, non-linear access to media.
Right.
Your choice, NVMe,
Right. So if you look at the acquisition cost chart that Rick had in the beginning from IDC, you were saying 5 point something X difference, right? That is for a typical enterprise grade TLC, QLC that you can, it's QLC that you can buy. I can go to a NAND supplier probably to look at, hey, how can I get it cheaper? What is your yield level? Are you throwing away stuff? Can you give me the cheap NAND, implement it? Let's say I take that. Let's say I take that really cheap NAND. I have some intelligent, magic on top, right? To use that NAND and make it cheaper. Does it work out cheap? Let's say I build a rack. Let's say a rack with 22 TB. Rick, you mentioned HAMR, and we've been thinking about it as well. So I have the numbers on top of my head. A warm storage rack with HAMR drives, 30 or 32 TB or 34 TB, ends up being around 18 petabytes. So if I were to build a cheap SSD with 18 petabytes, to use the read bandwidth that the SSDs offer, my rack will have to be sparse because the top of the rack switch becomes a limiting factor. The uplink bandwidth becomes a limiting factor. And for somebody that builds and operates their own data center, I think there are talks in OCP and probably even at-scale conferences on networking from Meta. We have a cookie cutter kind of data center to make it operationally viable. And this means our class network fabric is limited on uplink bandwidth. It's standardized on uplink bandwidth so that we can replicate it evenly. And as we upgrade it, there are generations where we upgrade the network bandwidth and it doubles. But when it doubles, we stuff bigger capacity drives in or we make use of it. So what we are getting out of that equation is my SSDs will be used similar to HDDs in a bandwidth per TB perspective. I will need to scrounge. It's a factor of reliability, weighing reliability versus cost. From our numbers so far today, even with the cheap SSDs, cheap NAND that we can find, cost-wise, it still doesn't work out. Acquisition cost-wise. Power-wise, yes, it is power-wise a little lesser. So if I'm really constrained on space, DC space, really constrained on power, I can stuff the rack and make even more than 18 petabyte possible with a cheap, let's say QLC, since we're talking about it. But the bandwidth per TB of such a rack will be worse than HDDs, given my network bottleneck.
So your throughput hits other bottlenecks, and
Yeah.
shift the bottlenecks and shift the cost.
And overall cost ends up becoming
So
problematic.
There's a gain you much because you have to deal with other bottlenecks.
Right.
To catch up.
Right. So if you look at the read bandwidth of SSDs, right, per SSD, I think Rick had a chart for read bandwidth and write bandwidth that was based on a specific workload. But let's say the way we operate, we have larger chunks, we have enough buffering, and the I/O that hits the hard drives is large enough. It's in megabytes, few single-digit megabytes. So at that point, we are streaming bandwidth. A hard drive can give me 200, maybe 180, 200 megabytes a second if I push it to its limits, random I/O, outer to inner diameter averaged out, whereas an SSD can give me way more, maybe 2 gigabytes a second, 3 gigabytes a second. So it can give me a lot more throughput. But if my workload is only looking for 1.5x of what an HDD can offer, this is way more of a cost to pay.
Yeah, so it's better fit.
Yeah.
Thank you.
It's okay. My question is more related about STA and SAS support for 48 gig. There is any updates or news about supporting the 48 gig?
No, right now, we're capped at SAS 4, which is 24 gig. You know, it's to be determined, but right now there's no active development on 48 gig.
Okay, that's great. I have another question, please. It's more about using the mixing in standard topology for SAS, mixing between SAS and SATA. What is the main intention for using SATA? Because SAS has more higher speeds, of course, than SATA, and also air handling, the FEC mechanisms, and all stuff for SAS handling the connections is better than SATA. Right.
Right. So historically, SAS has been an enterprise solution, dual port. SATA has always been the cheap drive option, or to be rightly saying the words, it's low cost option, not the cheap one, right? So until nearline came, right, at that point, I think I can tell this out. We never use dual ported SAS drives. We always use single ported SAS drives. So whatever cost penalty we paid for that was unnecessary. At some point, I don't want to mention the exact drive capacity. Both SAS and SATA had the same offering in terms of, okay, I have a single ported drive, I have the same feature set, I have the same controller even. PCBA stuffing options are different on the HDD. But now I'm looking at both these drives, which are identical and cost-wise, all of a sudden almost the same. But SATA has another advantage. If you look at volume shipments, which I don't know if any of these players publish this externally, IDC, Trend Focus, SATA shipments are way over in volume compared to SAS. And that enables another thing. There's a supply advantage. if my demand goes up suddenly for some reason, unforeseen reason, I can still get my capacity demand met with SATA much more easier than with SAS. So having that flexibility helps us a lot. All we need is capacity at lower cost. We don't care if it is this drive or that drive or that drive.
One more question. Did you compare MTBF between SAS, SATA, and cell fatigue?
I did not do that analysis. It would be an interesting one. I haven't done that.
Okay, thank you.
Woody?
So you kind of mentioned, what the drive guys call remanufacturing, right? In the field, remanufacturing, when you lose an edge and basically remanufacture the drive process, and then that allows the remaining user capacity to be usable, right? Is that something from a Steam perspective? Is that something you're going to try to drive at least a standard command, so that the three major spinning drive guys can all support that, or is that vendor unique, or how's that going to be handled?
So it was vendor unique, right? Somebody called it reman, somebody called it depop, right? But now T10 has intercepted that, and I don't know exactly what they call it in T10, but there is coverage for it in T10.
And that's just the standard command to send it down and tell it, and then all the stuff that happens with other covers is still vendor unique, essentially, on how they handle it? How it gets communicated there are a number of things that gets communicated back and forth to the drive. That's standard. How the drive does it, that's the sausage making. So. Thanks.
Okay, I get it. Hard drives, SSDs, it's not ready or time yet for the SSDs to come in and replace it. Got it. To me, it always seems like the answer when I look at memory hierarchy is it's never, should it be all SRAM or should it be all DRAM? The answer is it should be both. Yeah, that's most systems today are. Is that what the E1S drives are for in your warm tier, is to kind of store your hottest of your warm tier data, or is it used for something else?
It is for offloading the drives from fully utilizing the capacity. So this is related to how we manage the I/O capacity at a cluster level in the warm tier. So this is not for intelligent tiering that other cloud players offer. We have a rack SKU. I think it has been opened up. It's called Olympic. This is based on the Yosemite V3 based chassis. There will be an E1.S, plain E1.S chassis and a rack SKU. That the same tectonic tier runs on, software layer runs on that platform as well. So we have imagine a flash fleet or a flash based cluster as well as this HDD based cluster. The SSD inside the HDD based cluster is to absorb the P99 spikes that some of these HDDs may see in one-off systems, as well as to offload any read-heavy things that are cacheable locally. So our objects, when written to the software layer, are sharded across many drives depending upon the erasure code that we use. So if one chunk is bad or is reread or is read multiple times because there were multiple requests for it, I might as well cache it locally in that SSD. And maybe that partial chunk is what I need to serve the user data instead of reading everything. So these are for P99 spikes that the HDDs will take longer to process. We have that read cache locally. Hope that makes sense.
I think what I heard you say was it's not necessarily strictly just storing hot data, but you're sharding anyway, but
It's locally hot.
Shards might land on
Yeah.
NS drives for faster speed.
Yeah, it's locally hot data. Yes, you're right. Yeah.
Could you go back to that picture with 216 drives? Yes. Now I understand that I'm sure you have more than one NIC here. I'm sure that you have like multiple, like this is HA available. Have you ever had to deal with a double failure where you had to rebuild all of the data that was behind that system? And if so, how long did it take?
That's a good question. That's a good question.
Still building.
It is still building, yeah. It is still building. So this is, I think I can touch on it by making parallels with AWS cloud architecture. AWS has a concept of availability zones. I'm not sure if you're aware of it. So we also have something like that internally, and they're either related to a region or a small fraction of a region. It's a failure domain or something to that extent. So we have a failure domain as a fraction of a data center, and that can go down for proactive maintenance, maybe for a few hours, maybe for a day, right? And I mentioned that we shard our data across multiple drives. Let's take one common erasure code that we use. It's 10 data chunks, 4 parity chunks. Another one is 9 data chunks, 6 parity chunks. There are a few more ones, but these are the predominant ones.
So your striping is not just...
We take one disk from one rack,
Okay.
and then shard the data across racks. So if the whole rack goes down, I could care less. I can still rebuild the data. If the whole failure domain, which is multiple racks, goes down, I can still rebuild the data.
How long is that?
That,
If it's just a system here.
so if, for example, the failure domain concept that I mentioned, the reason I mentioned that is if it goes down for 24 hours, we call that a temporary unavailability event. That's why it's an availability zone. So we don't go and rebuild the data. We reconstruct it on the fly from the parity and serve it with the hope that in 24 hours it comes back. The moment it's lost, that's when we go and rebuild that chunk, or basically all that data in that failure domain. So typically, we don't see that happen. In the recent past, we haven't seen that happen also. And that's one of the reasons why proactive maintenances, definitely, proactive maintenances are really important to actually make sure that never happens. Right? Hopefully that answers your question. Yeah. And during that time, let's say that one chunk is gone, reconstructing that needs, I need to read all the other data chunks to reconstruct that. So I'm going to amplify my reads quite a bit. And during that downtime, there's going to be an increase in I/O on other drives. So instead of spoon feeding the queue depth, that's where CDL also helps the whole thing.
Remind me what CDL is?
It's a queuing mechanism. It's a latency-bound queuing mechanism. I can say this is important than that. This is less important. That is more important. The drive can optimize the I/O for us.
Is that part of the rate configuration you configure the topology? Handling the
Could you
the rate?
yeah.
I mean, is it one of the concepts that you use to manage the error handling system?
Yes. If let's say a sector is bad and it got reallocated, that would affect one object maybe, and it would be handled by that RAID or erasure code topology. Yeah.
In the previous so I was told that Tectonic is a sort of mental file system. So what's the relationship between the warm storage and Tectonic?
Warm storage, we call it, so if you look at what Meta or Facebook, when it was called Facebook, authored papers, there was something called warm storage a few years back. And that storage file system evolved into something else. So we didn't want to reuse the same name, we just rebranded it to Tectonic. So warm storage is the same thing as Tectonic. Internally for us, this is our warm tier, if it makes sense. It's the tier where we keep hard drives always on, and it's online storage, if it makes sense. And the cold tier, we actually turn off hard drives to save power.
At the scale large enough, do you eliminate the need for the flash array to store the metadata? So do you store the metadata on the actual SATA drives?
We used to, and that's actually a good question. We think it is inefficient to store metadata on hard drives. So we moved to, I should have mentioned, I forgot that Steven's question earlier on the SSDs. It's used for read caching, it's also used for metadata, local metadata. So SSDs are far better. They provide 1000x IOPS compared to HDDs on metadata. Yeah. So that's the file system local metadata. There's a metadata layer at the global object level as well. That's somewhere else. Yeah.
Okay. And we're getting the sign. So thanks for joining us this afternoon. Appreciate the time. I think it was a very good discussion. Thank you. Thanks, Monica.